Yes. In this video, we are going to derive the expression for the magnetic field along the axis of the circular coil which carry current. Right? Here, in this class, we are going to derive the expression for the magnetic field along axis of the circular coil carrying current. This is what the task what we have in this class. To find out the magnetic field, first along the axis of the circular coil, I have to imagine circular coil. This is what the circular coil. And this circular coil having a radius A. Right? In the circular coil, the current is moving flowing in the anti-clockwise direction. Right? In this circular coil, the current is flowing in the anti-clockwise direction. Whenever there is a current in a circular coil, of course, there is a magnetic field in the surrounding region. My aim is to find out the magnetic field along the axis of this circular coil. This is what the axis of the circular coil. Therefore, to show an actual diagram of this circular coil, I am selected a circular material. You have to consider this circular material as a circular coil. And this is a circular coil. This is what the axis of the circular coil. This is what axis of the circular coil. At any point, I have to find out the magnetic field. At any point on this axis, I have to find out the magnetic field. That is what the task what I have in this derivation. Now, to find out the magnetic field, first I have to consider some point on the axis. Let me consider a P is a point where I am going to find out the magnetic field. So, how you are going to find out magnetic field at P? Because of the current in the circular coil. This is what the question we have. And for that, I have a tool, that is what Biot-Savart's law. Biot-Savart's law, I am using Biot-Savart's law to find out the magnetic field at point P because of the current in the circular loop. Biot-Savart's law gives the magnetic field at some point R, that is dB, that is because of small current element. The Biot-Savart's law will give a small magnetic field because of a small element. But it do not give the magnetic field because of the entire conductor. It will give a small magnetic field. When you integrate this dB, you will get the magnetic field at this point because of the entire conductor. So, by seeing this, by keeping this in mind, I have to take some strategies to find out magnetic field at point P because of this circular coil. What is the strategy? Similarly, what they consider as a small current element, I am going to consider a small element in a circular loop, that is dB. dB is a small element. I will name that as an ideal. This is also current element. Now I am going to join this AB current element to the point P. This point P is at a distance x from the center of the coil, and the distance between current element and the point is R. And that R as a value by using this a square plus x square whole raised to the power of 1 by 2. Now, this line makes an angle theta with the axis of the circular coil. Now, for every current element, we have a diametrically opposite element in the circular coil, that is CD. And that CD has same current and same length. Thus, CD has same current and same length. Now, this is what having the same radius, and I have to join this current element to the point P, and that also has the same distance, or really R is equal to a square plus x square whole raised to the power of 1 by 2. Now, what is the direction of the current at this point? Sorry. What is the direction of magnetic field at this point? The direction of the magnetic field can be explained by using right hand palm rule. By using right hand palm rule, I am going to explain what the direction of the magnetic field at this point. According to right hand palm rule, if in this conductor the direction of this current is this is the direction of the current in this conductor. According to right hand rule, you have to place your thumb on the direction of the current, and this palm will give the direction of the length R. This palm will give the direction of your palm. This palm will give the direction of R. And when you curl your finger, the direction of your curled fingers will give the direction of the magnetic field. Right? You have to once again. This thumb will give the direction of electric current. This palm will give the direction of the R, and your curled fingers, the direction of your curled fingers is the direction of the magnetic field. is the direction of the magnetic field. So the direction of the magnetic field is this is inverse. The direction of the magnetic field is inverse. So by taking the dimension, if this is a conductor carrying current, I put my thumb in the direction of the current at this point. At this point, I have to find out the magnetic field. This is what the point P. This is what the point P. And this is what R. The line which is perpendicular to R will give the direction of the magnetic field. This is what the direction of the magnetic field. The line which is perpendicular to the direction of the R gives the direction of the magnetic field. Therefore, I will write the perpendicular line to the R. To R, I will write a perpendicular line that will give the direction of the magnetic field because of the current element AB. Similarly, what is the direction of the magnetic field at this point? Because of this current element is the perpendicular line drawn to R will give the direction of the magnetic field according to right hand rule. This is the right hand rule is one way to find out the direction of the magnetic field. We have another way, that is what if you write the Biot-Savart in vector form, you are going to find out the direction of the magnetic field. That is not necessary. By right hand rule, we have find out the direction of the magnetic field. So I am going to draw a normal to the x-axis. This is what y-axis. This dB makes an angle theta with y-axis. This dB also makes an angle theta with y-axis. Now, what is the magnetic field at this point because of this current element? According to Biot-Savart, I will write dB is equal to a small current element because of this small element is equal to mu naught divided by 4 pi I dl divided by r square into sin theta. What is the value of theta here? You know, theta is the angle between ideal and what? Line joining R, position or vector. This is R and this is what ideal. In this case, the direction of ideal is the tangent which is drawn to the current element will give the direction. This arrow mark will represent the direction, and this is what the direction of ideal or dl. This is dl and this is what R in this 2 dimension. If I take out of the plane for 3 dimension, this is the dl and this is the R. This is R. The angle between dl and R is 90 degree. You can clearly observe that the angle between dl and R is 90 degree. At any point, at this 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 point also, or at this point also, the angle do not changes. The angle is 90 degree. Therefore, I will consider that theta is equal to 90 degree. Sin 90 is 1. Therefore, dB is equal to mu naught divided by 4 pi I dl divided by r square. Call this is an equation number 1. Right? This is the value of theta. Now, this dB makes an angle theta with this y-axis. This is a vector quantity. I am going to resolve this vector quantity into 2 components. This dB has a 2 components. Along y-axis, along x-axis. In vertical direction, it has dB cos theta. Along the horizontal direction, it has dB sin theta. This dB also has 2 components. Along vertical direction, dB cos theta, and along horizontal direction, dB sin theta. Now, to find out the resultant magnetic field at point P, because of these 2 current elements, clearly listen, I am going to find out the resultant magnetic field. Because of only these 2 current elements, I have to add these 4 resolved components. When I add these 4 resolved components, instead of adding dB, instead of adding this 2b, I am going to add these 4 resolved components. I will get the resultant magnetic field at point P, which is in inverse direction, because of these 2 current elements only. I will write, so by adding this 4, I will get 2 dB sin theta. I will get 2 dB sin theta. This is what the resultant magnetic field at point P because of these 2 current elements. Then where is sin theta gone? Sorry, where is cos theta gone? Here, the cos theta, this dB cos theta is because of this current element. This dB cos theta is because of this current element. These 2 are in the same plane but opposite in direction. These 2 are in the same plane but they are opposite to each other. Therefore, the dB cos theta because of this current element was cancelled out by dB cos theta because of this current element. Then I will get 2 dB sin theta. The horizontal components become added up because they are in the same direction. They are in the same direction. Thus, they are going to add. They are going to add it up. This is the resultant magnetic field because of these two current elements. In our circular coil, in this circular coil, we have many DL components. We have many DL components or elements. For this DL, I have a oppositely diametrical element, this. For this DB, I have this. So, we have numerous number of DL elements or ideal current elements in this circular coil. For this DL, the dB cos theta, because of this DL, is cancelled out by this dB cos theta. But the dB sin theta, because of this current element, is added up by dB sin theta of this element. And similar process or similar thing is applied to every DL component. So, what I am going to tell you here that when I make the summation of dB sin theta, I will get the resultant magnetic field at this point because of the entire circular coil. Since the dB cos theta of all DL components become cancelled out. The dB cos theta component of all DL elements will be cancelled out, and the dB sin theta, which is in horizontal direction, or added up, and that will give the resultant magnetic field at this point P. Since it is in the same direction, therefore, summation of dB sin theta will give the resultant magnetic field at this point P because of the entire circular coil. Now we will do that. The resultant magnetic field at P, because of the current in the circular coil, is given by B is equal to summation of dB sin theta. We know the value of dB, that is mu naught divided by 4 pi I dl divided by r square into sin theta. I am going to convert this summation into integration. That is, integration over a circular loop is mu naught divided by 4 pi I dl by r square into sin theta. In the next step, I am going to apply the value of r square and value of sin theta. I will get, and I am going to integrate the dl component. First, I have to take constant outside, mu naught divided by 4 pi. Here I is constant, sin theta is also constant. From this figure, I will write what is sin theta. Sin theta is equal to opposite divided by hypotenuse r. Therefore, a by r whole divided by r square. What is r square? Here, r is equal to square root of a square plus x square. Therefore, r square is equal to a square plus x square into integration of dl Therefore, d is equal to mu naught divided by 4 pi. Here, I a divided by, here the value of integration of 2dl is 2 pi a, and this is a square plus x square into r. Now, d is equal to, here pi get cancelled, 2 1s are 2 2s are, mu naught divided by 2 I a square divided by x square plus x square whole raised to the power of 3 by 2. Since we know the value of r, that is a square plus x square whole raised to the power of 1 by 2, and here the basis of same power must be added. 1 plus 1 by 2 is 3 by 2. This is what the expression of the magnetic field along the axis of the circular coil. From this expression, we can able to find out how much Tesla of magnetic field is produced because of how much quantity of electricity is flowing in the conductor or is flowing in the circular loop. Right? This is an expression which we are using to find out the magnetic field along the axis of the circular coil. Now, we know the expression for the magnetic field at some point is mu naught I a square divided by 2 into x square plus a square whole to the power of 3 by 2. This is what the expression for the magnetic field at some point because of the current in the circular coil. So, if that coil having n number of terms, what is the magnetic field? That is B is equal to, just you have to multiply n to the numerator, you get mu naught n I a square divided by 2 into x square plus a square whole raised to the power of 3 by 2. This is what the expression for the magnetic field if that coil contains n number of turns. this is. Now we have two cases in this derivation. We have two cases. That is, first one case is when x is equal to 0. That means what is the magnetic field at the center of the coil? What is the magnetic field at the center of the circular coil? If this is a circular coil, I already told that this is an axis. We have already derived the expression for this point. On the axis of the circular coil, we derived the expression, and that is this is what that expression. So here the case 1 is asking to find out the magnetic field at the center of the coil. At the center is nothing but here x is equal to 0. Put the value of x in this equation, we will get B is equal to mu naught Ni A square divided by 2 into A square whole raised to the power of 3. Therefore B is equal to, here mu naught Ni A square divided by 2 into A cube. Here A square and A square get cancelled. B is equal to mu naught N I divided by 2A. This is what the expression of the magnetic field, or this is what the expression to find out the magnetic field at the center of the coil. At the center of the coil, what is the magnetic field? That was explained out. That was find out by this equation. And similarly, like this case 1, we have case 2. What is that case 2? Case 2. In case 2, if the point P is far away from the center of the coil, if this is an axis, at this point we already derived at center of the coil, or we already derived the expression for the magnetic field. Now we have to find out, our task is to find out magnetic field at the point P is far away from the center of the coil. At that time I will write x is so greater than A. Therefore I am neglecting A in the equation. When I neglect the equation A in the equation, that B is equal to mu naught Ni A square divided by 2 into x square whole raised to the power of 3 by 2. Now B is equal to mu naught Ni A square divided by 2x cube. This is what the expression used to find out the magnetic field at a point which is far away from the center of the coil. This equation can also be written in the term of magnetic dipole moment. That is how B is equal to mu naught Ni A square divided by 2x cube. I am going to multiply and divide this equation by 2 pi. Therefore, B is equal to mu naught divided by 4 pi Ni A square pi divided by x cube. This implies mu naught divided by 4 pi Ni A divided by x cube. This A is the area of the circular coil, and this Ni is what we known as magnetic dipole moment. Therefore, I will write B is equal to mu naught divided by 4 pi. Mu naught divided by 4. Here we have left with 2. This is 2. Here also 2. And 2m divided by x cube. This is what the expression for the magnetic field at a point which is far away from the center of the coil in terms of magnetic dipole moment. This is a magnetic field because of this magnetic dipole moment, and this is what the cases what we have in this derivation.